Well, let's do a few more examples involving the fundamental theorem of calculus. Just a continuation of this. So remember the process. Here's a pretty crazy looking one, right? What in the world's going on here? What is the value of this definite integral? Now this would be very difficult to do without the fundamental theorem of calculus, but with it, it's pretty easy. You do have to know the antiderivatives that come about with the trig functions. So you should know that the derivative of the tangent function is secant squared. And therefore you should know that the antiderivative of secant squared is the tangent function. So the antiderivative of secant squared is tangent. So 4 secant squared becomes 4 tangent theta is the antiderivative. Evaluated, right, at these limits, and you can see these limits are a little crazy. Right. So I'm going to factor this 4 out and then just evaluate tangent at 4 pi over 3 and tangent at 5 pi over 6. Now that's where, I was showing you before the unit circle, you'll need to be able to find the tangent, say at 4 pi over 3, right? 4 pi over 3 being down here. Remember, tangent is sine divided by cosine. So this divided by this. Negative square root of 3 divided by 1 is square root of 3. Okay. So this is going to be square root of 3 minus, and then tangent of 5 pi over 6. Right. 1/2 divided by negative square root of 3 over 2 is negative 1 divided by square root of 3. Or negative square root of 3 over 3 if I rationalize that. And that's what I'm going to do. So that's the same as 1 divided by square root of 3, right? Just rationalizing that. And so we see what we get. Exact value, again, is what we're looking here. Plus, right, square root of 3 over 3. And this is 3 square root of 3 over 3 plus 1 square root of 3 over 3 gives me 4 square root of 3 over 3 in the parentheses, right? Adding these together by finding that common denominator. And then I can multiply 4 times 4. And that's what I want you to give me, is the exact value. Okay, you can approximate this again, but you have to give the exact value. So for trig functions, you're going to need to know how to get the exact value. Sine, cosine, tangent, secant, cotangent, etc. from that. And there is a unit circle in the help sheets that come with our textbook, and I will make sure that you have access to that. Okay. All right, let's take a look at this example here. Now, change gears a little bit. We're going to find all the constants A, constants being real numbers, such that the integral from 1 to a of 6x plus 4 dx is equal to 0. Okay, so what's going on here? Well, let's take a look, first of all, at this integral, definite integral from 1 to a, 6x plus 4. Can I get an expression for this? I can. I don't know what a is, but let's see. How would I do this? What's the antiderivative of 6x plus 4? The antiderivative is 3x squared. All right. So hopefully you can do that pretty quickly. Take the derivative, I get 2 times 3 is 6x. And the antiderivative of 4 is 4x. Right. Okay. Having trouble with that, again, let me know, but that should be pretty easy now for polynomial functions. And the upper limit is a, lower limit is 1, so I'm going to evaluate this at a, so I'm just replacing x with a. I get 3a squared plus 4a, right? Minus, evaluated at 1 is going to be what? 3 times 1 plus 4, right? Which is 7. And so I get 3a squared plus 4a minus 7, right? So there's the value of it. So now that I have that, I can now answer the question, right? when is this definite integral going to be equal to what? 0. So when is 3a squared plus 4a minus 7 equal to 0? Right? Solve that equation. How do we solve an equation? Well, if you can set equal to 0, if I can factor this, that's the way I go. So can I factor this? If I got a 3a times a, obviously, by trial and error, you can do this one, right? 3a times a is 3a squared. And then negative 7 is prime, so it's got to be a 7 and a 1. One's positive and one's negative. So how is that going to work? You need to get positive 4a. Do it by trial and error. And what is it going to be? Plus 7 here, minus 1, right? So now, notice the first times first gives me 3a squared. 7 times negative 1 is negative 7. The outer is negative 3a. The inner is positive 7a. That gives me the positive 4a. And so I can answer the question, right? 3a plus 7 is 0 when a is what? Subtract 7 and divide by 3. Negative 7/3. Or, right, a minus 1 is 0 when a is 1. And so there are the values of a that make that definite integral equal to 0. All right, last example. What I want to look at is definite integrals involving absolute value. So this causes a little wrinkle. So we haven't talked about this. What would, the antiderivative from 0 to 3, and this is absolute value here. Absolute value here of x squared minus 4. Okay. So how do you do this? I mean, what's the antiderivative of the absolute value of x squared minus 4? Is it just, absolute value of what? The antiderivative of x squared is what? 1/3 x cubed minus 4x. Is it just the absolute value of that? No, it's not. Absolute value throws a little wrinkle. Let's take a look at it. Let's look at the graph of x squared minus 4. That's the parabola opening upward, right? Vertex is at 0, negative 4. It's basically x squared shifted 4 units down, right? That parabola shifted 4 units down. So there it is. What's the absolute value of x squared minus 4 look like? Well, it looks like this. Why? Because, right, all the negative outputs, what's going to happen to them? They're going to change to positive. So this 0, negative 4 becomes what? 0, positive 4, right? Pops up there. And this 1, negative whatever becomes 1, positive that value up here. So basically, it sort of reflects the negative portion about the x-axis, doesn't it? The positive portion stays the same. There's no difference, right? Because the absolute value of a positive number is just that positive number. Absolute value of 2 is 2. Okay? So this is the graph you have to look at. So now, when I'm graphing, notice that this portion right here, this portion right here is really a reflection of the graph of the original function, x squared minus 4, about the x-axis. How do we do reflections about the x-axis? We multiply the output by negative 1. So this is really negative x squared minus 4, which is negative x squared plus 4. That's this portion. Okay. So if I'm integrating this function from 0 to 3, so from 0 all the way to 3, notice from 0 to 2, right, this portion, I'm going to have to use this function, the negative 1 times x squared minus 4 function, right, going from 0 to 2 to integrate. And then from 2 to 3, we'll be back to the original function, right? So this portion here is just equal to what? The original x squared minus 4. So the key is you have to determine, for your graph inside the absolute value bar, when is it negative and when is it positive, and of course, where does it cross the x-axis? Because then we have to determine, well, if it's negative on the interval from 0 to 2, we're going to look at integrating negative 1 times the function. If it's positive on the interval from 2 to 3, we'll just integrate the function without the absolute value bars. Okay, so the bottom line is basically we were saying that x squared minus 4 is equal to negative x squared minus 4 for x on the interval from 0 to 2, right, which is this first portion here, right, from here to here. And it's equal to just x squared minus 4 for x between 2 and 3. And that's the idea, right, because whatever you input for between values of x between 0 and 2, this expression inside the absolute value bar is negative. So we have to change the sign, right? When I take the absolute value, if it's negative 3, it becomes positive 3, for instance, the output. Okay, so we basically have to split this up. Into those parts. And so what we're going to do is we're going to look at the part from 0 to 2, and there it's going to be negative x squared minus 4. And then the integral from 2 to 3 of what? Positive x squared minus 4. And the sum of these two, right, are going to give the answer. Another thing, when you do absolute value, because the graph will always be above the x-axis, the value of these definite integrals indeed is going to represent the total area of these two regions. So both of these integrals should evaluate to positive numbers. If you get a negative number for one of these, you obviously have made a mistake. Something is wrong. Okay. So we can do the nitty-gritty details now real quick here. Of course, I would distribute that negative through, as I did up there, negative x squared plus 4. So the antiderivative here is negative 1/3 x cubed plus 4x. And over here, it's just 1/3 x cubed minus 4x. Okay. Doing some plug-in, I get negative 1/3 2 cubed plus 4 times 2. Minus, evaluate at 0, well that's 0 and that's 0, so this is going to be minus 0. Okay. That's this first one. And then plus this one, which would be 1/3 3 cubed minus 4 times 3, minus 1/3 2 cubed. A little calculations involved in that. I get 2 cubed is 8. I get negative 8/3 plus 8. 2 cubed is negative 8/3 plus 8. And then over here, minus 0, it's just 0. 1/3, one of the 3's cancel here. I get 3 squared is 9. Right, 9 minus 12. It's negative 3. And this is 1/3 of 2 cubed, that's 1/3 of 8 minus 8. So this is minus, be careful under minus, 8/3 minus 8. Okay. This is, what 8 is 24/3. And so 24/3 minus 8/3 is 16/3. And here, oh goodness, what do we got? We got so negative 3. I would just say, go ahead and distribute this negative sign through. Negative 3 minus 8/3 plus 8, which is going to be negative 3 plus 8, 5 minus 8/3. 5 minus 8/3. So 5 is what? 15/3. 15/3 minus 8/3 is 7/3. Okay. But again, these two positive numbers are important, right? 16/3 was the value of the integral from 0 to 2. That's going to represent this, purple shaded in region. And then the second integral was 7/3. That is the area under this segment here. Add them together, we get the total area under the curve, right, which is the value of this definite integral. Okay, so that's how we deal with integrals involving absolute values. And that's sort of the end of our lecture on the fundamental theorem of calculus part 1. Next, we will talk about the fundamental theorem of calculus part 2, which gets a little interesting, and we will talk about that in the next lecture.